Okay, so last time we stopped here. So let's finish the slides. C-test for a proportion, since the normal distribution can be used to approximate the binomial distribution when NP is greater or equal than 5 and N cubed is greater or equal than 5. The standard normal distribution can be used to test hypotheses for proportions. The formula for the C-test for proportion is this one, right? Where P hat is the sample proportion, P is the population proportion, and N is the sample size. So make sure that Thursday, when you go to the test, make sure that you have a cheat sheet, okay? Okay, so let's do this, and let's do this somewhere else, okay? So here, let me copy this. Let's do that here somewhere else, here, okay? So here, they're asking you, a dietitian claims that 60% of the people are trying to avoid trans fats in their diet. So that's his claim. She randomly select a sample of 200 people. I'm sorry, she randomly select 200 people and found that 128 stated that they were trying to avoid trans fats in their diet. So the sample proportion is 128 divided by 200. And you simplify that and you get some decimal, right? 128 divided by 200, 0.64. Sorry, this is the sample proportion. And this is P hat and Q hat should be equal to 0.36. And let's see what else they're saying here. At 0.05, is there enough evidence to reject the claim, right? So is there enough evidence to reject the claim? So the claim says that the addition that 60% of the people are trying to avoid trans fats in their diet. Okay, so they're trying to avoid trans. So the true proportion is 60%, and then that means that the alternative, it should be not equal, right? Because they're saying 60% of the people are trying to avoid the trans fats in their diet. So trying to avoid and not avoid, right? So is there enough evidence to reject the claim? So the claim is here, right? It's 60, right? They said the 60%. Okay, so now we need to do the C-test, right? So we have P hat minus P square root of P Q over N, right? So C equals P hat, which is 0.64 minus 0.60, PQ 0.64 times 0.36, square root of N is 200, the sample size, right? And we need to compute this thing. So what is this thing? So calculator, right? You should get 1.17, right? Or 1.78. Oh, I'm sorry, 1.18. And you need to compare that with the alpha, right? Significance level. So this is 0.05. And let's see. Okay, so this is a two-tail test, right? So C-test, you know what it is, you should know by now what it is, this value. So that's 95%. So that's 1.96, negative 1.96, 1.96. So 1.18 is not in the rejection region. So we failed to reject. That's our conclusion, failed to reject. Therefore, we can say that there's not enough evidence. I mean, actually, yeah, there's enough evidence to support the claim, right? Because we are failing to reject. So there's enough evidence to support a claim. To support a claim that 60% of people are trying to avoid trans fats in their diet, right? So that's what you're supposed to say at the end, okay? Okay, so that's that part. Okay. Or you can say there's not enough evidence to reject the claim, which is the same thing, right? Okay, next example. Here you have this problem. Let's see what they said here. Okay, let's do this here. So a telephone company representative estimates that 40% of its customers have calling waiting service, right? So, okay, and to test this hypothesis, she selected a sample of 100 customers and found that 37% have call waiting, right? Okay. So for 100 sample, so this is the p hat, right? So the p hat is 0.37 and the q hat should be 0.63, right? And so this is we need to state the null hypothesis and the alternative hypothesis. So telephone company representative estimates that 40% of its customers have call waiting, right? So they have, okay, and the claim is, let's see, okay. Is there enough evidence to reject the claim? So the people in the company, the P, they're saying that this is 0.40 and they're supposed to be not equal to 0.40, right? Yeah, so the claim is this, right? A telephone company representative estimates that 40% of its customers have call waiting service. So having means that's the claim. To test the hypothesis, she select a random sample of 100 customers and found that 37% have call waiting, and at 0.01, right? Is there enough evidence to reject the claim? Okay, so again, C equals P hat minus P, and then this is PQ N, right? So this is P 0.37, this is 0.40, PQ 0.37, 0.63, and N is 100, right? And this is the square root of that. Okay, so let's do that. 0.37 minus 0.4, 0.37 times 0.63 divided by 100, square root of that. Okay, so equals to that, equals to this. This is negative 0.62, about that. And I need to calculate the C value, right? I need to compare this with the C value from the standard normal distribution. So we have 0.01, so that's 99%, right? So this is a two-tail test. So therefore, this is going to be 2.5a and negative 2.5a, right? So negative 0.62, it's not in the rejection region, it's somewhere in the non-rejection region, therefore failed to reject. Then your conclusion should be there's not a strong evidence, right, to reject the claim, right? There's not evidence to reject the claim. To reject the claim that to reject the claim that that 40% of the customers have a call waiting service, right? So that should be your conclusion, right? Make sure that you state that in your exam, right? Make sure that you stated that. Okay, so let's continue. Okay, so we finished with that, and now we have to do the chi-square for variance and for standard deviation, right? The chi-square distribution is also used to test a claim about a single variance or a single or a standard deviation. If you have just in case for your knowledge, right? If you have two, then you will have to use an F test, Fisher's test. And you have more, you will have to do an ANOVA test, right? So that's a different story. We're not gonna do that, so just focus on this. So the chi-square distribution is also used to test a claim. So you have your n is your sample size, your sample standard, your sample variance is s squared, and your population variance is sigma squared, right? Again, the chi-square, we have to consider the degrees of freedom, so don't forget that. Okay, so what is the assumption for the chi-square test for a variance or standard deviation? The sample must be randomly selected from the population. The population must be normally distributed for a variable under the study, and the observations must be independent one of another, right? So let's do that. So here they want you to find the critical chi-square value for 15 degrees of freedom when sigma is 0.05 and the test is a right tail test. So when it's a right tail test, you just look at this value in the table and the degrees of freedom of 15, right? So chi-square, 15 degrees of freedom, 15 degrees of freedom, and we said that it was 0.05, I believe. 15 degrees of freedom and 0.05, I believe we said that. So it's 24.99, okay? That's how you find it. Let me double check. They said 15 degrees of freedom and right tail test 0.05. Okay, so 0.05, 0.05, and 15 degrees of freedom. So that's 24.99. Okay. Okay. Let's continue. So here they want you to find what? They want you to find the critical chi-square value, 10 degrees of freedom, and alpha is 0.05. However, this is a left tail test, so you will have to do, well, your degrees of freedom is going to stay the same, but you have to do 1 minus alpha here. So this is 1 minus 0.05. So this is going to be 0.95. Okay, so you need to look at the table, this and this. So 0.95 and 0.05. 0.95. I said 15 degrees of freedom, I think I said, right? So 0.95 and 15 degrees of freedom. If that's the case, that's 2.72. So 10 degrees of freedom and 0.05, I'm sorry. 10 degrees of freedom and 0.05. Okay, 10 degrees of freedom and 0.05, so that's 0.95. So they should be 3.9, right? We double check. 10 degrees of freedom, 0.05, which says 0.95. So you should get this value, right? 3.9. This one right here. 3.9. Is the value. There you go. 3.9. Okay. Okay. So here they're asking you find the critical value for 22 degrees of freedom, right? And alpha 0.05. Okay, so not big deal. Again, so but this time we have to do because the chi-square is skewed to the right, right? Something like this. You need to find those values, right? So if you want to find the value to the right, you just put 0.05 and 22 degrees of freedom, right? But if you want to find the other one, you have to do 0.95 and 22 degrees of freedom. So let's find those values, right? So 22 and 0.05, 22 and 0.05, 0.0, so that's 1. And then the other one, 22 and 0.05, that should be here. 22 and 0.05, right? 22 and 0.05 is 1 here. And then the other one should be 0.05. Remember, we have to divide this by 2, right? That's the reason we need to split that, right? So let me double check again. So we said that it was 0.05. So, oh yeah, I just need to look for, let's do one step at a time. So 0.05, 22 and 0.05, right? So 22, 0.05, that's right here, 33.92. So that's one value. So this one should be 30, not that area. This one should be 33.92. And the other one, degrees of freedom 22 and 0.05. I need to look for 0.95 and 22, right? 0.95 and 92. Okay, 0.4, okay, and 95. So it should be 12.33, right? 12.33, because it's 1 minus that, right? I made a mistake. I'm so sorry. You need to do, I'm so sorry. You need to do, I'm sorry. Here you need to do, this thing. You need to do 1 minus alpha over 2. I forgot there was a detailed test. So this is 1 minus alpha is 0.05 divided by 2. So this is 1 minus 0.025. So I was right the first time. So this is supposed to be 0.025 here, and then it's supposed to be 0.975 here, right? So just the same thing. Degrees of freedom is 22. I apologize for that. So here I need to do 0.25, right? 0.25 and 22 degrees of freedom. 0.25, 0.25, 22 degrees of freedom. So 0.25 is 10.98, like I was saying before. 0.25, and I think it was 10. 10.98. So 10.98 and 0.025. That should be here. That's 36.78. 36.78. So that's the answers, right? So yeah, that should be the answers. Yeah. So let me explain that to you one more time, just in case you got confused. The chi-square test is a right, it's a skew to the right, okay? And if you're doing a two-tailed test, right, you have to do, since alpha is 0.05, you have to do, first, if you want to find this value, you just do 0.05, but you need to divide by 2 because this is a two-tailed test. So you divide by 2, so alpha over 2 should be 0.025, and the degrees of freedom is 22. So you need to look for 22 degrees of freedom and 0.025, right? And that's here, right? 22 degrees of freedom and 0.25. So that's right here, right? 0.25 and 22 degrees of freedom. On the right, you get 36.78. And to the left, it's just 1 minus this value, 0.025. And you get 0.975. And that's this value here. And you do degrees of freedom, 22. So that's 10.98. That's how you do that. Okay. Sorry about that. Okay. So the value is 10.98, and the other value was 36 point something, whatever that is, 36.78. Okay, that's how you find that. Okay, so when it's a two-tailed test, you need to do the divided by 2, right? If it's to the right or to the left, you don't need to worry about that. Okay, so let's do an example with the problem, right? So that's what we need to do. Let's see what happens here. Okay. Okay. So here an instructor wishes to see whether the variation in scores of 23 students in her class is less than the variance of the population. So 23 students, right? The variance of the class is 198, right? Is there enough evidence to support the claim that the variation of the students is less than the population variance sigma square of 225? So we need to state a null and alternative hypothesis, right? So what's the claim? Is there enough evidence to support the claim that the variation of the students is less than the population variance. Okay. So we have the population, right, is less than the sample. So here let me put this here clearly a little bit here. Okay, so we have the variance of the class is 198. So that's S squared, right? That's 198. And let's see what else is asking for. Is there enough evidence to support the claim that the variation of the students is less than the population variance? So let's read that one more time. Is there enough evidence to support the claim that the variation of the students is less? So the variation of the students is less than that, and the variation of the student should be bigger or than that, right? So under the population. Okay. So let's find out, right? Let's find out. Here they're saying, what else? Is less than the population variance, which is 225, right? 225. So we can use actually sigma here. So sigma is 225. They say that the population variance is less than 225 or bigger than 225. So that depends on the class, right? So that's what they're saying here. Okay, so just be careful when you're stating your null hypothesis. Is there enough evidence to support the claim that the variation of the students is less than the population variance? So this is the variation of the students. The variation should be sigma squared, and this is less than the population, right? And bigger than the population. Okay, so that's the claim. Now we need to solve the problem. So this is chi-square. Chi-square equals n minus 1 s squared. I'm sorry, sigma squared over s squared, right? So that's formula. So we need to compute. Actually, I'm sorry, I'm doing this wrong. So this is a sigma squared. So now you need to compute that. So n minus 1 is 22. The sample, the variation is course. Okay. Variance of the class. The variance of the class is 198. Okay. And is there another for the, okay, is the variance of the population is 225, right? So you just need to compute those values and that's it. 22 times 198 divided by 225, and you get 19.36. So now you need to figure it out. Which one was the claim? Okay, so the claim is that the variation is less. So this is the claim. So this is a one-tailed test, right? So we need to compare that with a one-tailed. So it's less. Okay, so what is the significance? The significance is 0.05. Since this is one tail, right? We just need to look at 0.05 and degrees of freedom, which is 22, n minus 1, right? Degrees of freedom is 22, 0.05, and we look at the table and we find out what's the value. So 22, 0.05. And we said that it was less, right? Yeah, so less means to the left, right? And so that means we need to subtract then 1 minus 0.05, which is 0.95, right? So it's 0.95 and 22 degrees of freedom. 0.95 and 22 degrees of freedom. So this is 12.34. 12.34, 12.34. So the chi-square value is 19 something, right? So 19 should be in the non-rejection region, right? Because 12.34 is to the left, so that should be in the non-rejection region. So we failed to reject. So fail to reject, right? So we will say, therefore, we can say there's enough evidence to support the claim that that the variation of the students, that the variation the variation in scores of the 23 students in her class is less than the variance of the population, right? So that's what you need to say, right? I'm gonna save that to save time, okay? So that's what you will need to say. Be careful when you're doing the test and when you're using your formulas. You need your formulas to use to solve the problems, right? Okay, so that was that problem. Okay, so here they should say sigma, right? That's the claim. Let me see if I have the same. Just want to make sure. Yep, I have the same. Okay. The same, yeah. So they have here, there's not enough evidence to support. Yeah. So there's not enough evidence to support a claim that the variation in the scores of distress is less than the variation. So let me see what I wrote. Actually, there's enough. Okay, I said there's enough evidence to support the claim. Okay, that's good because we failed to reject. So that's good. Just want to make sure. Okay. So next problem. Okay, let's do this one. Okay. So here, a cigarette manufacturer wishes to test the claim that the variance of the nicotine of its cigarettes is less. Okay. So that's a claim. So the claim is the alternative, right? It's less. The variance is less than 0.644. Okay. Nicotine content is measured in milligrams and assume that is normally distributed. A sample of 20 cigarettes has a standard deviation. So this is a sample standard deviation of 1 milligram. Okay. And at 0.05, is there enough evidence to reject the claim? Reject the claim of the manufacturer's claim. So this is the claim. So the null should be the reverse, right? Okay. So again, this is a chi-square test. Okay, so we need to use the chi-square formula. So this is n-1 s squared sigma squared, right? So n-1 is 19 s squared. So this is the standard deviation. The standard deviation is 1, but remember the variance, we need to square that, right? So, I mean, 1 to the second power, that's not gonna affect nothing, but just saying, if it was a different number, you will have to do different, right? So sigma square, what is the population standard deviation here? Let's see, what is that? Sample 20, standard deviation. Okay, here is the standard deviation, 0.644, right? 0.644. I was looking for that. Okay, 19, 0.644. So 19 divided by 0.644, you should get 29 point something, right? 29.5. So now you know that this is a right one-tailed test, right? Chi-square test. So we need to do less than, right? That's what they're asking here. Manufacturer wishes to test the claim that the nicotine of his cigarettes actually cigarette manufacturer wishes to test the claim that the variance of the nicotine content of its cigarettes is. Oh, okay. So that's not right. So this is supposed to be equal and not equal, right? So it's equal should be here. This is the claim. And this is the alternative, right? Because they say a cigarette manufacturer wishes to test the claim that the variance of the nicotine of its cigarette is. So that should be on the null. Okay, so everything else is the same. So we need to do a two-tailed test, right? For the chi-square test, we need to do a two-tailed test. Okay, so that's the chi-square test, and we need to compare that with the values from the table, right? Okay, so this is a two-tailed test. We have a 0.05, right? So we need to divide that by 2. So first, we need to do alpha 1 minus alpha divided by 2. 1 minus 0.05 divided by 2 is 1 minus 0.25. So that's going to be 0.975. Okay. And that will imply that that's the, okay. So the 0.25 is this part, and the 0.975 is this part. So degrees of freedom is 20. No, degrees of freedom is n minus 1. Degrees of freedom is 19. So that's right here, right? So we need to look for those values and then compare with these things, right? With the test value, right? So, okay, so let's see what we get. So 0.975 and 19. 0.975 and 19. 0.975 and 19. So that's 8.9, 8.91. So this is 8.91. And then the other one should be 0.025 and 19. 0.025 and 19. So that's here, right? And that's 32.85. 32.85. 32.85. Okay. And we'll get 29.5. So that's in a non-rejection region again, right? So we failed to reject again. So failed to reject. Failed to reject. So we can say that there is enough evidence to support a claim of the manufacturer that the variance of the nicotine content in cigarettes is 0.64, 0.644, right? So therefore, there's enough evidence to support the claim, right? So you will be with this because this value is in the non-rejection region, right? So let's see what they did. It's the same thing I have. Did not reject. So same thing. There's not enough evidence to reject the manufacturer's claim that the variance of the nicotine. Same thing, right? Okay. So there's not enough evidence to reject. So we stay with that conclusion. So here you have additional topics regarding hypothesis testing. There's a relationship between the confidence interval and the hypothesis testing. Well, that's very obvious. When the null hypothesis is rejected in a hypothesis testing, the confidence interval for the mean using the same level of significance will not contain the hypothesized mean. Likewise, when the null hypothesis is not rejected, the confidence interval computed using the same level of significance will contain the hypothesized mean. Okay, so let's see an example here. Okay, let's see. Let's do that. So let's do that here. Let's do that here. Okay, so sugar packed in 5-pound, sugar is packed in a 5-pound bags. An inspector suspected the bags may not contain 5 pounds. Okay, a sample of 50 bags produce a mean, okay, produce a mean of 4.6 pounds and a standard deviation of 0.7 pounds. Is there enough evidence to conclude that the bags do not contain 5 pounds as stated at 0.05? Also find the 95% confidence interval of the true mean. So we need to say the hypothesis first. So they're saying that inspector suspected that the bag might not contain the 5 pounds, right? So the mean is not equal to 5. And then the alternative hypothesis should be, okay, a sample video, okay. Is there enough evidence to conclude that the bags do not contain 5 pounds as stated? So the alternative should be, I'm sorry, this is supposed to be equal. This is not equal. Okay, so this is the claim of the inspector, right? So now we need to do the hypothesis testing. Let's see what's happening after that. So we can do a C test here. So this is x minus mu over sigma over square root of n, right? Okay. So we're gonna use the sample standard deviation in this case because we don't have the population standard deviation here. Okay, so x is 4.6, the mean is 5, the standard deviation is 0.7, n is 50. So let's compute this. 4.6 minus 5.7 divided by square root of 50. So you should get negative 4.04, a big number. Okay, so we need to do a 95% confidence with that significance level. This is a two-tailed test, so obviously this is gonna reject, right? So this is 0.05 or 90 also, so 0.05. You have to divide by 2 and all that stuff. But since this is a C test, I know that 95% or level of significance of 0.05 means 1.96 here and 1.96 here. So see, this is an extreme value we reject, right? Because it's in the rejection region. So we reject the null, right? We reject null. So reject the null. So we should say there's enough evidence. There's enough evidence to support a claim, right? To support a claim that the sugar bags, they do not contain 5 pounds. Okay, but that's not the end, right? Here they're asking you also find a 95% confidence level, right? So you know how to do that. So that's x minus c, the c over 2. And in this case, we have to do this way because we don't have the population standard deviation. So we have to do mu and we use these values, right? Copy, paste. So we need to find the confidence level, right? So x bar equals 4.61, right? And minus, this is 1.96 and s over 0.7. And this is 50, and the same thing applies to the other side, but with different sign, right? So this is minus and this is plus. So let's do that on the other side as well. So this is plus. Let's see what happens after that. Okay, so 1.96, 7 divided by 50. The square root of 50, by the way, don't forget, this is square root of 50. This is also square root of 50. Okay, so times 1.96, and then this is 4.61 minus this number. So we get 4.42, the mean, and let's see what happens on the other side. 1.96, 0.7 divided by 50 times 1.96, and then this is 4.61 plus this, we get 4.04. And notice, as they said before, right? When you since we reject the null here, that they said that the bags they contain they do not contain 5 pounds. Notice that this value right here, the mean of 5 pounds, it's not within this interval, or it's not within the confidence interval. Therefore, we can say that what? We can say that that's true what they're saying, right? So there's a relationship between the confidence interval and the hypothesis testing, right? So they agree, both agree that the bag is not within this range, right? So therefore the bag does not contain the 5 pounds as mentioned in the problem, but we don't know if it contains less or it contains more, right? We just know that it should be, the range should be between these two values, right? Right? That's what they're saying. Okay, good. Okay, let's finish this. They said reject the null. What is their null here? Yes, we reject the null, right? Because the null, you know that it's not 5 pounds, right? It's something else. Okay, good. So here they said, notice that the 95% confidence interval of M does not contain the hypothesized value of that, because as we mentioned, there's a relationship between those two, right? Hence, there is an agreement between the hypothesis testing and the confidence interval, right? So if we reject the null, then that value should not be in this interval, right? And this is the last line. Finally, we arrive here. So power of statistical test, the power of a test measures the sensitivity of the test to detect a real difference in parameters. If one actually exists, the higher the power, the more sensitive the test. So basically, the more power you have, the more strong the test will be, right? So here I wrote some stuff. Power is rejecting a false null hypothesis, right? Which is what you want, right? You want to reject a false null hypothesis, right? So it's the what? It's the complement of a type 2 error, right? Because when the type 2 error, we say fail to reject when it's false, right? So it's just a complement, and sometimes we define that as 1 minus beta, right? So this is power, 1 minus beta, or basically 1 minus type 2 error. And we said before that beta is the type 2 error. So 1 minus type 2 error gives you the power of the statistical test, right? So usually they, once you have the significance level and your power, after that you can you can find your sample size and things like that, right? So your beta, your type 2 error should be as small as possible, as I wrote it here. And power basically is the ability to make the right decision, right? So because we are rejecting a false null hypothesis, that's right, that's absolutely right. That's what we want to do. And this is it from the slides. Okay, so type 1 error means reject when it's true, right? And type 2 error means fail to reject when it's false. When you are either in this case or in this case, you're making the right decision, right? Don't accept the no, right? Because we don't accept no's. We just say fail to reject, right? And that's basically it. Thank you and have a good night. And I'm gonna try to post the other part as soon as I can. Thank you.